Hello, so welcome to Math2526. So this is class C3. Okay, the topic for today is many sample problems. So we just discussed the two sample problems. Right? So a typical example for two sample problem is just like we compare two classes, lots of performance for two classes. Right? So here we have this evidence like for class 1 average exam score for average exam score is 84 and the class 2 is 81. So 84, we know 84 is better than 81. So we have evidence, right? So but we wanted to check whether this evidence is strong enough or significantly. Okay. Okay, so here we have two versions for two sample test. We can assume here is for variance. Variance is we can believe they are equal or not, or was this assumption equal, or do not make this assumption. So why we need to assume the variance equal? The idea is we have 2 sigma 1 sigma 2, so we say if sigma, we replace them by s1 s2, then we have some trouble, like we say things like do not follow t distribution, or we have some theoretical difficult. Okay, so if sigma 1 sigma 2, we assume sigma 1 sigma 2 are equal, so here we have only 1 sigma, right? So replace this 1 sigma by 1 s, so this s is sp, reported standard deviation. Then we say this z will become exact t. Okay, so here we need to check whether we assume we have this assumption, right? Variance equal, not equal. So here suppose like we do not make this assumption, so without this assumption, then this test statistic is this, right? X bar minus y bar, so s1 square over n1 plus s2 square over n2. Okay, so then with this like a test statistic, so we have this number of 1.22. So how can we determine this 1.22? This number, this test statistic is big number or small number? So here we just check. Let's say so here we can roughly we can use this t distribution. Okay, degree of freedom is we just pick a smaller one, right? Degree of freedom. So we have 2 degree of freedoms. One is 24, the other is 19, right? So we just pick a smaller one. Okay, so that's equal 19. Then if we regard this is a distribution, so we just check this cutoff point for degree of freedom for 19. Let's say 19 t19, and we just find this cutoff point. This is 005, 1 till 5, 005. So I remember this cutoff point is 1.729. So we can say, this number is small number, right? This is small number. So we can say their difference is not so significant, not so big. So the decision is HO, right? Or mu1, mu2, quite the same, no much difference. Okay, so go back to answer this question. Can we say class 1 performs significantly better than class 2? So we say no, class 1 do not perform significantly better. So looks bad, but not so significantly. Okay, so this is a two sample t-test. Okay, two sample problem. Okay. I included this is a t-table here, so we can check again. Let's confirm that the degree of freedom 19. Okay, and 1 till 005. Yeah. Okay, 1 till 005. Right. So we have this number. So this number is a critical value, right? 1.729. Yeah. Okay. Okay. So today's topic is many sample problems. Like here we have suppose like a Math 2526. We have 4 classes. So we have those information like okay. So for each class we have the average exam score and the class size. So we call this sample size, sample mean, and sample standard deviation. Okay. So we find that we have the evidence say class 1 the score is higher than other 3 classes, right? So the question is the same. Can we say class 1 performs significantly better than other classes? Like suppose I teach class 1, I really wanted to say that, right? My class performs significantly better than other class. So I say I have some evidence, but you will ask me like whether your evidence is strong enough, right? So we just check this strong enough or significantly or significance. Okay. So here this is compare. This is many sample problems. So for many sample problems, we have to make this assumption. Assume the values are equal. Okay, so here we have sigma 1, sigma 2, sigma 3, sigma 4, right? We have 4 values. So if 4 values is the situation, general situation is too complicated. So we assume they are equal. So just have 1 sigma. Okay. So for many sample problems, this is our basic assumption. We assume values are equal. So why we make this assumption? Just for simplicity, right? So if we do not make this assumption, the situation is too complicated. We cannot handle. Okay. So now we have this question. So what is poor variance? So the idea is the same. The poor variance is just the weighted average of those values. So weighted on what? On degree of freedom. Okay. So in this case, we have 4 standard deviation of 4 values. So what is poor variance? Or what is poor standard deviation? So poor variance is the 7 square, 9 square, 8 square, and 6 square. We have those 4 values, right? 9 square, 8 square, 6 square. So we want to find their weighted average. So weighted on what? On their degree of freedom. So degree of freedom is n minus 1. So this minus 1, right? So we have this 7 square weighted on 24. 9 square 19 weighted, right? So 8 square, 21, 22 minus 1, right? So 6 square, 20. Then divide totally, add them up, right? So this is poured variance. Okay? Okay. I'm sorry. There's a second question. Yeah. So there's our first question. We say we assume variance is same, equal. Okay. So we say like here, we wanted to compare the 4 groups. So we say we can compare one by one, like compare class 1 with class 2 with the 2 sample t-test. 2 sample problem. Like compare the 2, compare that 2, compare that 2, right? We can use this way, right, to compare the 4 groups. Okay, so it seems 2 sample t-test, we can work here, right? We can compare each pair. But the question is, we cannot. Can we use 2 sample t-test for check many sample problem? We say answer is no. So why no? Why we cannot do that? So reason is like suppose we compare mu1, mu2, we find mu1 equal mu2, and mu2 equal mu3, and mu3 equal mu4. Okay, but so if we get this mu1 equal mu2, mu2 equal mu3, mu3 equal mu4, but we still cannot say those 4 mu's are the same. So why? So we say in mathematics, this is really clear. This is true, right? Mu1 equal mu2, mu2 equal mu3, and mu3 equal mu4. Saying mu1 equal mu2, mu2 equal mu3, mu3 equal mu4, right? But in statistics, we say this is wrong. So why? Because in statistics, equal means not exactly equal, just means quite close. So let's say, like we say equal, like if there's 2 numbers quite close, like x minus y is less than 0.1, we can regard those 2 numbers quite the same, equal, right? So in statistics, no exact equal. So equal means quite close. Okay. So now let's say, so suppose I use this. So let's say suppose this is 1, and we have these 2 numbers like 1.05. So those 2 numbers equal, right? Okay. So 1.05 and 1.10. These 2 numbers we also can regard equal because their difference is less than 0.1. Right? Okay. So 1.10 and 1.15. These 2 numbers we also can regard they are equal. But we can say, but 1 and 1.15 are not equal, right? Okay, so for this reason, we cannot use 2 sample t-test to compare many samples. So for many sample problems, we need to use a new method. We call this new method as ANOVA. Okay, so remember, for many sample problems, we use ANOVA. For 2 sample problems, we use t-test. Okay. So what is ANOVA? Okay. So at first we say many sample problem is just like in general, like we have data, we have sample 1 data, sample 2 those data, sample, we have k samples, like k sample k data like that. So here what we wanted to do, what we wanted to check, we want if we have like a k groups, we wanted to find the best one, right? We usually want to find the best one. Okay, so this is our purpose. If we have many, we want to find the best one, right? If we have 2, we also want to find which one is better. We need to find a better one. So if we have 3 or 4, many methods, many groups, we want to find the best one, right? But before we check who is the best one, we need to check this, whether all them have no much difference, whether they are essentially they are the same. If let's say if HO is true, then no best one, right? So if we wanted to find the best one, at the first we need to check whether they are quite the same or not the same. If they are quite the same, then we can pick each method. Each one is okay, right? So no best one, right? So if we just reject the HO, we say, oh no, they have some difference, then we need to check furthermore. We need to check whether this is and this is that is different, this is better than this, or whether then we can check whether we have the best one, right? Okay, so this is a many sample problem. So at the first we need to check HO equal or not equal, or not all are equal. Like maybe we can have some of them can be equal, but not all of them are equal. So here HA is, we can say just not HO. HOs all are same. So HO is not all are same. Have some different between them, among them. So this is for many sample problems. Okay. So for many sample problems, we say we will use ANOVA, this method. Okay. So what is ANOVA? So we say ANOVA is just the analysis of variance. Analysis of variance. We just pick this head letters, like ANOVA. Okay, so ANOVA is equal analysis of variance. So what analysis means? So here analysis means we separate whole variance into parts, into this part, that part. Then we just check, oh, those variance change, right? Changement. So we wanted to know where the change come from. From this way, we just check the source of changes. There's the change from this part, this way, or from that way, from this leasing or from that leasing, right? Okay. So for variance, here we just talking about the samples variance, not population. Now, population variance we don't know, right? So we have data, we can find samples variance. So for sample variance, we have this formula, right? If you like one sample, like we have this data, then how can find the variance? Just each one xi minus x bar square, then divided by n minus 1, right? So this is just like a one sample problem. Okay. Okay. So here we just for many sample problem, we just put those data together, just like one sample problems. Just put them together. Okay, so we have those data, so we can find these values, right? Okay. So we denote these values. So here xi means all those numbers. So minus x bar. So x bar is average for all. And so we denote this as SST. So here values we split into numerator or denominator. So we call numerator part is SST. So SST meaning stand for sum of square of total. So this is SST. Okay. So analysis of values means we split SST into two parts. We split SST into two parts. So this story just like that. We have group 1, we have the data, right? And group 2, we have those data. And here group K, we have those data. So their total values, total SST. So values we just focus on SST. So total SST, we find we can have just two parts, like changing from this direction. So between group to group, so suppose this group 1, group 2, or sample, group 2 or group K. Okay, so change in this direction. So this changing means just come from group to group. This is group 2, yeah. Okay, so such such change of such a ST we denote as SSG. So this SSG we just say, assume there's a change only in this way, there's a direction on. So this means on this way, no change. So no change means so those numbers no difference. So we just replace those numbers by group average. So replace, so SSG just calculate this way. Is we just suppose the data like in this direction no change. So we just replace the data by group mean. Okay. So for those numbers that no change, no change in this. So only change that come from this way, right? So this is SSG. Saying we need to find this change in this direction. So in this direction, the SSE we call this. Like okay, so those numbers have some change. So this SST is each one minus their average square, right? So here also just do the same way. So this is SST or SSE. Okay, so ANOVA meanings we can split SST into the two parts, this direction and this direction. Okay. So then, how can we determine their group to group have a difference? So we say like if SSG is big, like, so here we can say like if SSG is big, then we say group to group have difference, right? So then we will reject HO. Okay, so we believe they have not all this group to group have difference. So if SSG is small, right? If this SSG is small, then we can say HO is true, right? So no much difference in this direction. The changement is small, so we can believe group to group no much difference, right? Okay, so the question now is, we have the SSG, so how can we determine this big number, small number, or just determine the significance? Okay, so we need introduce this test statistic. So we call this number as F value. This test statistic F value. Okay. So we cannot judge SSG only. So we just check SSG over SSE. But so we say we want to check this number like relatively big or relatively small. So here we also need to divide by their degree of freedom. So SSG is degree of freedom and SSE is degree of freedom. So once we divide by degree of freedom, then by the way, so we denote this as MSG. So here become MSE. Okay. So here M means mean, average, right? Mean. So mean in statistics is just divided by degree of freedom. Okay. So what is the degree of freedom? So let's say, so here degree of freedom. So for SST, so we put all those data together. So degree of freedom n minus 1. So here n is, we just count total, put all numbers together. So how many like data like that, put them together as one sample problem. So we find the total number is n. So n minus 1. So this degree of freedom we also can split into two parts. So degree of freedom or SSG. So remember SSG, we calculate SSG is we assume this way no difference. So all those numbers the same, numbers the same, so numbers the same. So essentially we have a K group, so essentially we have K numbers, right? Okay, so K numbers, so degree of freedom n minus 1, so we have thus. So degree of freedom for SSG is K minus 1. So total degree of freedom, so this is K minus 1. So total degree of freedom is n minus 1, so we find this should be n minus K. Okay, so we split degree of freedom also into two parts. So we can find this cutoff point F value. So determine this big number, small number, so we need to check F table. Okay, check F table. Okay, so from this F table we can determine this value is big number, small number. Then we can make our decision. Right? We can make our decision. So decision is just like that. If we find this number small number, then we say no much difference. If this number is big, then we say have difference. Okay? Okay, so this is many samples ANOVA test. We call this ANOVA test or F test. Okay, so ANOVA test and an F test. So here is quite the same. ANOVA test or F test. So for test we have Z test, T test, F test. So it depends on like which table we need to check, right? To determine there's a cutoff point or test statistic is big number, small number. Okay. Okay, so now So let's use this. So we just introduce this ANOVA. So let's use a simple example to explain this ANOVA. Okay. So let's check a simple example for ANOVA. So now suppose the data, we have 3 samples, 1, 2, 3. So we have 3 groups, right? So group 1 data is 1 to 3. Okay. That's group 1. And group 2, so 4, 5, 6. So group 2. And group 3, 7, 8, 9. Okay, so now let's find SST, SSG, and SSE. So SST is we put those data together, so looks like a data like that. And so X bar for those data is 5, right? So SST is just each number minus 5, then square. So this number, first number, 1 minus 5, that's 4 square. Then second number, minus 5, 3 square, right? So 3 squares, or then 2 squares, then 1 square. Then 0 square, right? 5 minus 5. Then 6 minus 5, 1 square. So 7 minus 5, like that, 2 square, 3 square, 4 square, right? So we find this equal 60. So this calculate this number is this is just actually 2 of them. So for this one is like for this is 1 plus 4 plus 9 plus 16, right? So equals 30. Okay, so SST equals 60, right? Okay, so what is SSG? SSG is SST in this direction. So we assume in this direction no change. So all change doesn't come from in this direction, right? So in order to make sure there's no change, then we just replace the data like this, like this 2 group 1 become 2 to 2. So in this way, no change, right? Valence is 0. And group 2 become like a 5, 5, 5. We just replace the data by the group mean, 5, 5, 5, and 8, 8, 8. Right? Okay, so if the data like this, then is in this direction no change, so only in this direction, right? So this is SSG. So we say SSG is just like the SST, but the data looks like those data, right? For this data, find SST. So we say SST for those data. So such SST is SSG. So use the same idea. So SST is just each one minus 5, right? So 2 minus 5, average 5. So 2 minus 5 square, 2 minus 5 square, 2 minus 5 square. So this is just 3 of them, right? So 3 times 2 minus 5 square. And 5 minus 5, 0. So forget it, 0. So a minus 5, a minus 5, right? So we have 3 of a minus 5 square. So this is like 3 times 3 square, 9, 27, 27. So we get this 54, right? So you got this 54, right? Yeah, so 54. So what is SSE? So SSE is the valence in this direction. So this is SSE, okay? In this direction, just okay. So like 1 to 3, the valence from 1 to 3, and the valence from 4, 5, 6, and then from 7, 8, 9. So from each group. So values for 1 to 3, such as 3 numbers, this equal, let's say, like values 1 to 3. So in this direction, right? So this values, so average for them is 2. So each one minus 2, right? So 1 minus 2 square. So plus 2 minus 2 square, plus 3 minus 2 square, right? So this is, I think it's 2. 1, 0, 1, 2. Okay, so here the same story, like 4, 5, 6. So values for this 3 number. So average 5. So 4 minus 5, 5 minus 5, 6 minus 5 square. So this is also 2, right? So, and here, like, so 7, 8, 9. So for these 3 numbers, average is 8. So each one minus 8. So 7 minus 8, 8 minus 8, 9 minus 8. So each one is 1. So we find ACE equals 6, like 2 plus 2 plus 2. So we find in this example, or this is true, right? We can confirm this. We say what is SST here? 60. What is SSG? 54. What is SSE? 6, right? So we find this 54 plus 6 equal 60, right? So this is, we find SST equal SSG plus SE. So this is ANOVA. We separated ST into 2 parts. Okay, so this thing, test statistic F value uses formula. Okay, so SSG 54, SSE 6. So what is DF1? DF1 equal 2. We compare 3 group, right? So 3 minus 1, 2. Then we say total degree of freedom. We have 9 numbers. The total degree of freedom is 8. So then there's a degree of freedom DF2, or degree of freedom in denominator is 6, right? Okay, the F value equal 54 over 2 divided by 6 over 6. So we find it is 27. Okay, so now we want to determine there's 27. So here's 0. Okay, so 27 is big number or small number? So we need to find the cutoff point, right? So we say this is F critical value. So we denote this as F star. Yeah. So if F star is here, so we say 27 is big number. If F star is here, like then 27 is small number. So we need to find F star first. Okay. So this F star, we need to check it from the table. Okay. A critical value. So use this value, we will determine this 27, this cutoff point is big or small. Big number or small number? Okay. So let's check F table. So here I think I included the F table. Okay, so this is F table. Okay. So here for F table, we have 2 degrees of freedom. So we denote this as, let's see, so like DF1, DF2. So some F table call them a degree of freedom in numerator or degree of freedom in denominator. Okay, so here this is degree of freedom 2. So df1 equal 2. Okay, so there's 2 degree of freedom. I remember there's 2 and 6, right? So numerator degree of freedom of numerator is 2, degree of freedom in denominator is 6. So we just find, so this is the cutoff point of F critical value. Yeah, so degree of freedom 2 here. So those numbers of degree of freedom df1. We just split this way. Okay, and here degree of freedom df2 is 6. Okay, so 6, the 2, 6, we find this number. So this is a critical value, like 5.1433. Okay.哦，一个披风。No, okay. Okay, so now we can make our decision. So use this number. So let's go back. So F star equal 5.14. F star equal 5.1433. Okay, so we just basically just use this number as our cut point to judge big number, small number. Okay. Okay, so we say like here is small, so number a big number, right? So 27 is here. So we can say 27 is big number. Okay, 27 is big number. Then means the 3 group, their difference is significant. Okay, so for this problem, our purpose for this compare the 3 group is just check whether the 3 group have a difference or no difference. So here our conclusion is these 3 groups have difference, right? Yeah. So by the way, if we just by the average is like first one average 2, second group average 5, so the one average 8. So can we? So questions: can we say they have a difference? So we say we believe they have significant difference. Okay. So this is ANOVA for this simple example. So those data are very, very simple artificial data. We just make things simple. Just use this simple data to explain this ANOVA, right? So I hope you understand this ANOVA, right? So then our purpose, like our purpose for this problem, right? We want to compare these 4 classes. So can we say class 1 performs significantly better than others? So for such a problem, we leave this problem to next class, next video. Okay, so we can stop here, and so see you. Hope see you next video. Okay, so thank you. So we can stop here.